start. So my name is Borek Pacak from Czech Technical University, and it's my pleasure to welcome you on the first MMP webinar on generic platform design. It's the first webinar in a series of 3 webinars on MMP project that will be given during this and the next year. So let me first shortly introduce the MMP project. MMP stands for Multiscale Modelling Platform, and the goal of the MMP project is to develop an integrated modeling platform targeted especially to multiscale and multiphysics problems. The platform should allow natural integration of existing simulation software or data repositories as plugins. The integral part of the project are the 2 case studies, one focused on modeling processes of photophore light conversion in LIDs, and other on modeling CIGS film processing on photovoltaic devices. The MMP is a part of EU Multiscale Modelling Cluster and has been funded by EU under FP7. And for more information about the project, its aim and activities, please visit its website mmpproject.eu, where you can find more detailed information. The content of today's webinar is following. We begin with the platform design, starting with introduction of fundamental object-oriented principles. Next, we will present the overview of fundamental classes, the basic building blocks of the platform. These top-level classes enrich the Python language, which is used as a scripting environment to develop simulation scenarios. This part will be finished by an overview of key features of the platform. In the next part, the distributed and parallel capabilities of the platform will be reviewed. And the last part is devoted to short demonstration on how to install the platform and how to run simple examples. The webinar will be closed by the discussion, but feel free to ask any questions during the webinar. The webinar is split into 2 parts, as indicated on the right-hand side. The first part will be presented by me, and the second one will be presented by Víc Milauer. So let's start with the introduction to the object-oriented design. So what is object? An object is a representation of an entity in a model space. One of the key characteristics of the object is that it encapsulates attributes and methods. The attributes generally describe the object state, and the methods are used to query and manipulate the object state. And finally, class is a description how to create a new object. So the object is an instance of a class. So consider car as an example. Class would correspond to Volkswagen Golf car type, and the object is a particular car with its owner and plate ID. Car is a complex system which is composed of many parts, as you can see from the picture below. The parts are attributes of the car. Some parts may be represented by other objects as well, like the engine, etc. Methods are the commands that can be used to operate the car. Of course, the selection of attributes and methods depend on the problem. It will be different if we are going to develop a registration system for cars or whether we are going to develop a car simulator. As car is a complex system, we as a potential users need a simple interface that hides all the complexity of the car and allows to operate. In the real world, the problem is, however, more complex, as we have different types of cars. And naturally, there is a need for generic common interface allowing to operate any car. This interface in object-oriented language is called abstract interface. In real world, abstract interface is represented by a steering wheel, the pedals, and by the joystick. In programming language, that would correspond to methods allowing to turn left, right, accelerate, decelerate, etc., as is shown on the next slide. So in this slide, the relation between the real-world object and its object-oriented representation is shown. Here, the object is represented graphically as a rectangle with attributes and method sections. So in this case, the car is characterized by attributes like the engine, gear, number of wheels, plate ID, and its owner. Its method allows to start and stop the engine, turn left and right, and perform acceleration and deceleration. An important feature of classes is that they can form hierarchies to express the similarity between them. For example, bus is a specialization of general car, allowing to transport more passengers. So we can utilize inheritance by deriving bus class from a car class. The bus class will inherit all attributes from the parent car class and services. But it can add additional attributes and methods to characterize the bus and also redefine those inherited from car. So like adding a new attribute that tells us how many seats the bus can have. So let's summarize the basic terminology we have used. The object is a representation of any entity in the modeling space. Class is a definition of the object. Object is an instance of the class. Object is an encapsulation of the data. It means the attributes and methods that operate on the data. The object can be manipulated and data exchange using only the methods. So the attributes could not be changed from the outside. This has the advantage because the methods, they can ensure the consistency of the attributes. Classes can form hierarchical structure, allowing to describe the similarity or a kind of relation, inheritance between the classes. And the abstract classes define public interface to be implemented by the derived classes. And this concept of the abstract classes defining a sort of interface that has to be implemented by other classes is very important feature of the MMP platform, as we will see next. Now we move to our specific problem of designing an integration platform based on interacting distributed objects. We have chosen Python language thanks to its fast and efficient scripting capabilities and availability on virtually all platforms. The core of the platform is built on Python, extended by new high-level classes. The key feature of the MMP platform is that the abstract classes are not only representing simulation tools, but also other complex objects in the model space, such as properties, fields, units, etc. As a result, the platform defines interfaces for all these components, allowing to manipulate particle instances using generic standardized interface. The communication with individual objects using generic interface also allows to naturally abstract and hide all implementation details, including internal data and storage formats. Additionally, the platform supports concept of distributed objects where communication with remote and local objects is fully transparent. Okay, let's move now to an overview of fundamental abstract classes of MMP platform. So the first one listed here is the application class, which represents a base class for all classes representing simulation codes. It defines generic methods to get and set the data, such as properties and fields, and methods to update state in given solution step, request critical time step, terminate simulation, etc. Derived classes represent individual simulation tools. So for example, in our project, we have classes representing a microS or MMP ray tracer simulation tools. The next abstract class representing high-level data is a field. It represents a scalar, vector, or tensor quantity with spatial variation. The spatial domain over which the field is defined is represented by a mesh class, which is an attribute of the field. Field provides methods for evaluating its value at a given spatial position, basically. A property is an abstraction of a quantity which has no spatial variation, and the methods allow to set, get property value, its units, etc. We also have a abstraction for an expression depending on spatial position, time, and other variables, and this abstraction is called function, which could be also exchanged between the applications. As already mentioned, the spatial domain is represented by a mesh class using a collection of vertices and interpolation cells for its description. Derived classes represent discretized domains using different techniques like finite elements, finite volumes, finite differences, etc. Vertices or vertex and cell collections are used to describe discretized spatial domains. Vertices define geometry of cells, and they are characterized by their spatial positions. Cells, they represent a part of spatial domain and provide interpolation services over its volume. The platform now already contains implementations of many finite element-specific cell types in 2D and 3D. Time step is a representation of a solution step, and units is a class representing any unit as a combination of basic SI units. It allows to test for the compatible units and provide services for unit conversion. So as an example, I'm going to show an example of definition of an application class interface consisting of the methods shown in the following table, which continues on the next slide. The method signature, it means the name and arguments, are shown on the left, while the complete description, including type and meaning of all parameters, is shown on the right part of the table. All derived classes representing individual simulation tools have to implement this interface. So this allows end user to treat all applications using the same interface without, let's say, being concerned about the internal details of individual applications. So we start with the constructor, which has the name init. Is used to initialize the application. This process is highly application dependent, so here it's assumed that the problem description is provided by domain expert in application specific input file. Then we have the generic methods to get and set properties and fields. These can be input or output parameters or results of simulations delivered by other applications. Then, on the next slide, we have a method to update solution state to the next time step, a solve step method. Methods to request critical time step. Assembly time within a time step, services for terminating application, and services to query interface version, which has to be implemented by all application classes. This short list is only a subset of the application interface, and the detailed specification of all abstract classes and their interface is a part of a public project documentation and is available as a deliverable 1.1 interface specification. So if you are interested, you can find all the details in this report. So let me now go through the main features of the platform. In most cases, these features are direct consequence of the adopted approach, but we think it's important to stress them as many of them make the platform unique. The concept of abstract interfaces for applications as well as for high-level data allows platform users to manipulate these components using the generic interface, allowing not only to treat all applications in the same way, but also to treat different data representations, like what we have here in the picture below, where we have a field representation using the FEM discretization, but also we have a field discretization using the HDF datasets. But all fields can be manipulated using the simple single interface. So the abstract interface represents public, visible part of the implementation for the platform user, while the hidden implementation specific part should be visible only to the particular component developer. One of the key advantages of the MMP platform is that the high-level data are represented by classes as well, as mentioned already. As a consequence, the data exchange between individual applications is done by means of exchanging components or objects and not by exchanging complex raw data. And the advantage is that the high-level data representation encapsulates the data and the algorithms operating on the data. So the individual applications do not have to interpret the complex data structures by themselves. They basically receive the data and algorithms operating on the data. And this has, of course, several advantages, including a natural support for multiple data formats because they are all hidden behind the same interface. We have a less numerical errors due to the data translations and consistency because we have data structures and algorithms defined together on one place. And this means also the efficiency because the algorithms operating on the data have to be implemented only once in the object or component, but not by all individual applications that have to interpret the data. The advantage of passing data and algorithms operating on the data is particularly important in complex simulations, where the complex data structures have to be transformed somehow. Typically, for spatial data represented by the fields, the individual applications typically use different discretizations. One application can be, for example, finite element based, while the other finite difference based. Or the meshes can differ, as the error requirements are different for individual applications, for example. And so the data have to be transformed. So we need algorithms that operate on the data and allow us to evaluate the spatial data at given positions and so on. So it's important that as a part of the data, the algorithms are the integral part of it. Another typical case is that the individual applications use different types of elements with linear and quadratic interpolation, for example. And therefore, different integration rules are needed. And this may also require to evaluate the field variables at different positions. And it's not only the interpolation of the data, but certain quantities have to be treated with care as they have to satisfy conservation properties, for example. And this requires to use tailored mapping procedures. And all this complexity can be embedded into the components representing the complex data, making the data exchange much simpler and consistent. Okay, so let's move to the next slide with the additional features. Additional features include the persistency, which is the capability to store and restore all objects on a persistent storage, the support for units that can be attached to the data, and embedded security, where all the remote communication can be encrypted. In the case of distributed scenarios, platform provides tools for resource allocation and monitoring, and the platform can not only, let's say, operate in distributed environments, but it can also take the advantage of parallel processing by running the task that can be concurrently processed in parallel. This is typical for, let's say, multiscale simulations, which are outlined in the below part of the slide, where results of the macro level simulations are used as a boundary conditions for microstructural simulations in individual representative volumes, which can be independently performed in parallel. As already mentioned, one of the advantages of the MMP platform is the transparency of remote communication. Let me now explain how this is achieved and what are the advantages. So let's consider a simple simulation workflow consisting of two applications, application 1 and application 2, where the application 1 delivers the data to the application 2. In the local case, both application instances are executed on the same computer, so they can communicate directly, and there is no problem to realize that kind of the communication. In the distributed case, which is shown below, individual application instances are executed on different computers. So application 1 is executed or runs on that computer, while the application 2 is on the remote computer. So therefore, some communication mechanism is needed. In MMP, we use a concept of remote proxies. The proxy, which is shown here, is a local representation of remote application. It is created on computer running a simulation workflow. So this is this computer in that case. The proxy is a special kind of object that acts as an actual local object. It basically intercepts all the calls, forwards them towards the remote object, and passes the results back. So the role of the proxy is to hide all the details of remote communication, and basically the proxy acts as a local object. So this communication between proxy and remote object is hidden to the platform user. The key advantage is that the workflow code developed for the local case will work for the distributed case as well. The difference is only in the initialization, where instead of creating local instances, the corresponding proxies have to be created. So to summarize that first part, in MMP platform, we use a Python language which is extended by introducing a high-level classes allowing to easily model complex simulation scenarios. Python itself brings in powerful scripting environment with many existing modules for scientific computing. The simulation scenario or workflow is basically defined as a Python script developed by a domain expert. The graphical user interface workflow editor will be also available, but later during the project. And one of the key advantages of the scripting interpreted language is that it allows for really interactive computing, allowing on-the-fly interaction with the simulation. Parameters can be adjusted on the fly, data can be visualized, etc. Okay, so now I will switch to Beat, who will give the second part of the presentation. So let me switch to Beat.
Okay. Good afternoon, everyone. I hope that you can hear me. Božek, is it okay?
I can hear you, but I will mute my microphone right now. So
okay, excellent. So as Božek was saying, if you have any questions which are really important, just ask them immediately. Otherwise, there will be block of discussion at the end. So I hope that I'm sharing my screen right now. So I'm going with the second part, considering installation and simple examples. First, we have to say that we have quite heterogeneous group of users with different level of expertise, from people knowing only MATLAB to people knowing C++ and all different languages. And also, we are working on different platforms and operating systems. It's not just Linux and Windows, but it's also Macintosh. So we are trying to focus installation of this platform to all of these operating systems and users, and to give them some guidance how to proceed. So first, if you start looking for MMP platform, you basically find the name MuPIF, which is the abbreviation for Multiphysics Integration Framework. And MuPIF, it's also the name of all the packages and modules that we are using in the Python. So, of course, this goes through some development. So we have to keep some versioning of this MuPIF system. So currently there is version 0.11.5, which means the first is major, the second number is minor, and the third one is a patch. Basically, we should approach to alpha version at the end of this project, which is roughly within 1 more year. So that will be version 1 point something. But now we are still in such low numbers, so don't be surprised, because this is still, I would say, a major product, and we still need a lot of feedback and fine-tuning and debugging. So if you look, what is the structure of the MuPIF directory? So you install the MuPIF, and in principle you see other subdirectories, and they are also filled by different file names. It has some meaning. The most important where actually the platform is installed, it's under MuPIF, where you have all of these objects and classes, as Božek was talking about, like mesh, application, field, etc. And also you have the init file, which defines this Python as a module. Then you have, for example, the documentation. There is user and reference manual. The reference manual just lists all of these methods and functions. It has over 40 pages. There is also a user manual, which shows basic operation of this platform, which is also slightly updated. Then we have the directory with examples. There is about 15 different examples running in the local setup to the distributed setup. A lot of these examples are routinely tested every day, so we are sure that this platform is somehow working. So they are used as a test as well. And there is the subdirectory with tools. There are some, say, supportive tools which are sometimes used. Also, there are files just under the MuPIF top directory. The most important is setup. And this is used for setup tools because we don't install everything from one repository, but we can also use another feature which I will show in the next slides. So this is the typical scenario of what we are experiencing. So we have developers, we have users, so they are working with this MuPIF module. Of course, they have own code that they are using to join together, or to say send and receive some data between different applications. And then we have some storage of this MuPIF, so we can say that we have the repository, GIT repository, which is the protocol which is used here. And this is considered more to be the development branch. And then we have a Python installer server, which is, I would say, more user-friendly version, how to download the whole code. So we have, in principle, two major ways how to download the whole MuPIF installation. It's either through Git repository or through pip server. So now let's look to particular installation. We can, for example, first look to GIT repository, where we basically store the most recent and up-to-date version, which is the most important for developers because they need some synchronization and keep in touch about different problems. Anyone can download from this, and just developers can upload, so the repository doesn't get up messed with this some versions which don't work, etc. So this installation is very simple. It's used GIT command. It works on Linux and Windows as well, and you are basically cloning the repository to some directory, for example, MuPIF.git, which will download everything. So I will switch now to the screen, and it's very simple. So I will just type here git clone and then the repository to MuPIF git. It has roughly 10 megabytes of data, including all the documentation, and the whole structure of the files will be downloaded here. So I'm sure that people who are working with this MuPIF already know this way, how to take with that. So it's downloading. So now we have it here. So we may look what is under the directory. So you see the structure which is here. Here's the setup UI. There we have the MuPIF directory. And under the MuPIF, we have all of these different classes and definition of these classes. For example, examples are quite interesting. So we have here about, say, 15 examples which can be somehow tested. So now, if you go back to MuPIF, you can, for example, call Python. So if you are in Python, you can import the MuPIF very easily like this. So you import the whole module as it is. Of course, it works just from this directory because it has to find where it's located. So this is a more developer version, but also people who want to try something. This is kind of very simple. So this is the first way how to install the MuPIF code. There is the second way how to install. The second way goes through PIP. I hope I can switch to the next slide. Okay, sorry, it was too much. It's right here. So this is a more user installation. The classical question, how can I install it? And users are looking for some simple solution. So people around the Python, they created the Python package index, now stores over 64,000 different Python modules. So you don't have to search over the whole internet over one module. This installation, of course, needs root privileges because it installs somewhere to the system. For example, under Linux, it's under somewhere user local, etc., where normal user cannot write. And by default, the installation is included in the path which is search for these Python modules. In principle, it can be accessed from anywhere. So if I go back to the screen, I have to switch to be the root, and I simply type pipe install MuPIF, and it will search for all dependencies. You may also see here that, for example, we are searching for example, Pyro4, which is the required module, and even with this version. So all these dependencies are automatically satisfied, and they are downloaded as well. So once you got it downloaded as this, then the whole module MuPIF, it's accessible from anywhere. So even if you open the Python here, you can write import MuPIF, and you got it here, although you are somewhere completely else. So of course you have to be careful if you have more installation, actually which installation is loaded by default. So these are the two ways of installations, the developer installation and say the user installation. Of course, there is a little bit more around the installation. For example, you can look for the web interface. The web interface, okay. The web interface reviews what has been uploaded and also the history of the project. So you can, for example, look to the code. That again, you see the structure. You also will see who uploaded what kind of version, what was changed, etc. with some comments. So you can keep some history. So, for example, we have here dependencies which were missing before. And there is another feature important for us, which are so-called tickets, which means if you find any bug, you can type it here and somebody will look over that. We have open tickets, we have closed tickets, so the problems that were already solved, and of course people have different wishes, so also you can type them into these tickets on the Salesforce repository. So that was what was around, and I think now we have some time to show a few examples how basically it runs. So I selected 3 simple examples. The first example comes directly from the repository, which is example 01. And I just took the core of the code to see how the MuPIF platform operates. So now what we are trying to get the data from one application, pass them to application 2 and average them. So it's, we would say, very simple approach. Now everything runs locally, so you could write it even in much simpler way. But the point is that you can leave the same structure even if you are using the remote object, the distributed version, as Božek was talking about, so the code would remain the same. Just this @1 will be proxy of a different remote object. That's the only difference, which you don't see actually in the code. So the structure is, again, very simple. I'm not showing all of these definitions, but you can look to this example 1. But in principle, you solve some problem 1, we generate some of the data, you get the data to some local variable, you set this property to application 2, then in this function you have the averaging procedure where you average and then you print out the value. So you can run it pretty easily. So for example, I can go here to examples. To examples. MuPIF example 01, and that's the file. So you can just run it as Python example 1, and this is what you are sending, and so this is the output from application 1, and this is what the application 2 is printing as the average. So that's one of the most simple example directly included in the distribution. So then we can move to a little bit more, for example, difficult examples. I will just show the result. You can, for example, because you have mesh and you have field instances of classes, so you may also show, for example, mapping of these fields, which typically you need if you use different discretization of space, for example. So you can have again some application which defines, for example, such function, and you want to map this to much coarser mesh, which is here in the color. So we generate another mesh, and then you can just very easily to read the values in the new mesh, because you are using evaluate function, which is by default declared already in the application class, and it will look whether you are at nodal points. If not, it starts to interpolate the values. So this is all done in the background. So I just create the list of the values, and then you simply write them to the mesh 2, which is right here with all these values, and you can save the results to, for example, VTK output file example 2. So again, this is the core of the code, and if you visualize that, you see that there's the mapping from application 1 to the mesh 2. Okay. The last example is a little bit more complicated. Again, I try to do something very simple. So first, we have some value in application 1. We pass this value to application 2, and in this application 2, we multiply it by 3. I'm showing this as a local scenario, so we don't get into the distributed version so far. But again, the distributed version will have absolutely the same structure. We will just change the definition. Instead of app2, will be instead of object, it will be a remove object. So how does it work? Again, from application 1, we have to get the value, which is somehow there. We set this value to application 2. Then we solve, which means in this case we multiply by 3. And we will print out the value. Typically, such kind, if you want it as an example of more files, you need in principle 3 files. The first file is something that runs so-called name server, which registers all these applications. So if you have two remote computers, they have to know of each other. They can be behind firewalls and wherever else. So this name server just keeps the information where are the applications located. Then you have two applications. Again, they can be on two different computers. And then you have so-called steering script. This is the part of the steering script which asks for property or solves the step, etc., which basically controls and steers all the applications. So I'm running all of this locally, although you can do it very easily over the distributed network. So let's go to our example. So I go to simple example, and here first I have to run the name server. So the name server is right here. It gives me all different information what is running. You see also that this is running locally on some port, which is registered with this Pyro name server. So we have the name server. Then of course we have to run the server, which is the application 1 in this case. And the third terminal we will use for running the steering script. So let's write here scenario.py. So and here you have the logs. What happened? So we first connected to the server port, to the name server. We found the Pyro remote object. And we pass the value, multiply by 3, and get back the result, which is 6. So you can easily modify such local example to distributed example, where all these applications run on different machines, and this is the classical setup which will be used and is used further in MMP platform. So far, thank you for your attention. And I will hand over to Bořek. Just let me see.
Okay, so I hope you can hear me.
Yeah. Okay.
So let me go back. So thanks for listening. I just want to point out that let's say the whole webinar has been recorded, so you can go to it later at any time, and the link to video will be available soon on the MMP project website. And before we will go to the discussion, I just want to announce 2 remaining webinars. The second webinar on the with the title "Build Your Own API," which will be given in January 2016 with the following content. The first, we will give an overview of application interface, and then we will discuss different approaches how to implement application interfaces. One of them is the direct approach, where which means like directly communicating with the application, or indirect approach, which can be used with the closed source codes, and we will show both approaches on examples. And in the third webinar, entitled Perform a Platform Run, which is planned for May 2016, we will outline the platform prerequisites and installation. We will introduce a sandbox problem, which is going to be still defined. And we will show how to prepare the simulation scenario for sandbox problem using the GUI or Python scripts. And we will show the live demo, showing how to execute the simulation scenario, how to monitor the simulation scenario, and how to get the results. So now we will be pleased to answer your questions if you have any. So please, looking forward to your questions and comments.
So I'm Warwick, that's all, that's George.
Yeah, hi George.
It was a very nice presentation, and I really like the idea of the introduction to the object-oriented stuff for non-experts. So I think I got the spirit. The idea what I saw is that you've got one object which is called property, and if you could go back to that slide, the others could perhaps listen.
Yeah, I will try. You mean this one?
I do not see your slides now.
Okay, I will try to share my screen. Well, let me see how to do it. You don't see my screen.
So anyway, perhaps I can ask you that as well. So as far as I got, you've got the class property, which just returns a value which is the same over, which has no spatial variation. Yeah. So now we so my thoughts now, as you know, are turning around this HDF5, which somehow decomposes the simulation domain to certain hierarchical structures, which are the cells. We are aware about that. And the property you define here would be the property of the overall RVE. But now we would also need properties of, let's say, specific areas in the simulation domain, which could be grains or features in the simulation domain, or ensembles of features as defined, for example, in green 3D. So that would be phases. So is there any idea to, let's say, to expand these base classes further?
Yeah. We are aware of this, and we already have, let's say, additional attribute at the property level, which we call object ID. So the property can be attached to a particular object, like the crystal in the RVE or etc. So you can have a property attached to the specific objects in your RVE, I would say, for example.
Yeah, that would be great. And then we must even extend it. Let's say that we must have properties being attached to classes of objects. So that the example would be a number of different grains all belonging to the same phase. So then we have to define something like the property of the phase.
Yep. I think that would be, this is, from my point of view, is, let's say, how the object ID is interpreted as a property attribute. It could be like the ID of a crystal, or it could be an ID of a collection of the objects, etc.
Yes.
Okay. Any other question, comment? If no, I want to thank you again for listening, and please stay tuned. And we are really looking to see you and to join our other two webinars as announced during the project period. So thank you very much, and wish you a nice day. Bye bye.
Thanks, Borek.
Okay, thank you.
Bye bye.
Thank you. Bye bye.